good afternoon, or good evening, if you're joining us online. Um, Your Excellencies, dear colleagues, ladies and gentlemen, welcome to UNIDIR's Technology and Security Seminar on Cloud Computing, Exploring Implications for International Security and Governance. My name is Federico Mantellassi. I am a researcher here at UNIDIR at the Security and Technology Program. Before we start, I just want to take maybe a few minutes to first of all thank the speakers who will be joining us throughout the day, the EU for their gracious funding, and for my colleagues at UNIDIR who have helped with this event, Ms. Wenteng He, Ms. Sarah Grand-Clément, Ms. Jessica Ascaraga, and to you who have made the time to come to our event today, both in person and online. I want to take a moment when we start for some scene setting, both for what the event is, sort of why it's structured the way it is, and for what the topic is, why we're speaking about cloud computing today. So today's event is the first of a series, which we're calling Technology and Security Seminars that are focused on enabling technologies. These events comprise a technology breakfast, which kind of serves as a technology 101, and then a multi-stakeholder dialogue. Bring together the relevant stakeholders to explore international security and governance implications of emerging technologies. So through these events, the idea is that the multi-stakeholder community gets an opportunity to learn about a critical enabling technology, understand its international security implications, and explore governance possibilities. So the event today is structured in these two parts. First, a technology breakfast from 10 past 10 to 10 past 11, where we will go over what cloud computing is, but also putting it in the context of AI development. Second, we'll have a coffee break, and then we'll start our multi-stakeholder dialogue from 11:30 to 2:30. We will start with the first panel from 11:30 to 12:30, where we will look at the international security implications of cloud computing. We'll serve a light lunch just outside from 12:30 to 1:30, and then we'll have a second panel from 1:30 to 2:30, exploring the governance implications of cloud computing. At UNIDIR's Security and Technology Program, we take a holistic approach at researching the nexus between technology, disarmament, and international security. So this means looking at enabling technologies, or the constellation of technologies upon which other innovations depend, which also carry with them international security and governance implications. Cloud computing is one of those critical enabling technologies. It forms the backbone of modern IT infrastructure. And most of us use the cloud, we use cloud computing in our daily lives. Without realizing, we tap into and benefit from an intricate system of technologies, both hardware and software, which makes up the cloud on a daily basis. Cloud computing is also foundational to other technological fields. AI, for example, doesn't exist in a vacuum. It exists in a complex ecosystem of these enabling technologies. And in this ecosystem, cloud computing plays a vital role, delivering the computational power to develop and train the complex algorithms at the frontier of AI. In these contexts, the importance of cloud computing is only set to increase. As a growing number of industries turn to AI-enabled solutions, access to large amounts of computing power becomes paramount to train ever larger and performant algorithms on immense datasets. In the military domain, armed forces are steadily turning towards cloud computing solutions to power their increasingly digitalized, autonomous, and AI-enabled capabilities, making cloud computing an ever more important aspect of national security. While cloud computing provides enormous upsides, powering much of our technological development, it also carries with it some potential downsides. Geopolitical tensions, disruptive technology proliferation, systemic cybersecurity risk across society, market concentration, and environmental risk are only some of the potential downsides of increasing cloud reliance. The recently adopted Global Digital Compact aims to foster an inclusive, open, safe, and secure digital space that respects, protects, and promotes human rights. As more and more sectors come to rely on the cloud for their digital needs, understanding these risks and exploring how the various stakeholders involved in cloud computing can come together for the good governance of the technology is therefore vital to creating the safe, secure, and resilient digital environment. As a bit of housekeeping, please keep in mind the event is recorded, but the Q&As will not be. So without further ado, I will now turn to our first panel, introducing our speakers. So our first session will serve as a technology 101, providing this foundational knowledge to support the discussion that will follow. We will go over what cloud computing is, peeling back the different layers of the technology which makes up the cloud. But because here we're talking about enabling technologies, it's important to contextualize them. And so we will give you an overview of the global cloud computing landscape and discuss what role it plays in the development of artificial intelligence. So for this, together with us for this first panel, we have Dr. Babak Falsafi joining us here in Geneva next to me, and Ms. Zoe J. Hawkins, who I believe is online. Yes. Dr. Babak Falsafi is a professor in the School of Computer and Communication Sciences at EPFL and the founder of EcoCloud, an industrial academic consortium at EPFL. Ms. Zoe J. Hawkins is the head of policy design in the Tech Policy Design Center at the Australian National University. Each of our panelists will deliver a short presentation, and then we'll have time for some Q&A. So if during the session you have questions, if you're online, please do drop your questions in the Q&A, and we will ask them to our speakers. So I think that's enough for me talking for the moment. Babak, I'll turn to you first. I think we can project his slides.
I can advance using this.
Slide.
All right, good morning. Hope you can hear me. Okay, good. My name is Babak Falsafi. I'm a professor of computer science at EPFL and founder of EcoCloud. I'm also founding president of SDEA, which is a nonprofit in Switzerland data center efficiency association. We quantify and certify emissions and energy efficiency in data centers. So this are just a few slides on cloud computing for people who don't really know much about computing. So next, please. Okay, so what's going on in the world of computing? Roughly about, I think maybe a decade and a half ago, we had the era of big data. And the era of big data was enabled by the proliferation of computing environments. We managed to build computing and massive infrastructure globally available. And this allowed us to now collect data and monetize it, right? So data volume, data growth rate, finding ways in which you can turn that into value and eventually impacting GDP. And that has happened now for about a decade and a half, roughly speaking, worldwide. And the latest sort of transition in this monetization is now AI. Next. What enables, so what enables this ability to monetize data are data centers. Okay, so data centers are utility plants that are everywhere. They come in various scales. The idea is to build massive infrastructure at the lowest cost possible, benefit from the economies of scale. And the scale of the infrastructure itself can vary from tens to hundreds of megawatts. This particular one you see, it's a digital map, satellite map of Microsoft data center in Virginia. It's 200 meters in one dimension, 2 kilometers in the other dimension. The actual image is not up to date. It's been like this for the past 10 years for security reasons. But if we populate this with data centers today, if the whole thing was running, it would be roughly around 300 megawatts. And that is the electricity consumption of the city of Zurich. Okay? And what do we do with this? Well, we build them in areas where we have access to electricity, network, and cooling. So those are the three things you need to build them. In Europe, we build them also near heat recycling networks. So heat recycling networks are becoming quite popular in Europe. We have the ability to build them, and that heat that we get then that's generated from that 300 megawatts in this particular case, we'll recycle that into other uses for industrial use or for residential use. So, next, please. Okay, so what is cloud computing? Cloud computing is basically the computing that becomes available on top of the data centers. Okay, so you cannot talk about cloud computing without talking about data centers. And cloud stands for Common Location Independent Online Utility on Demand. So that basically means that once you build the data centers, you connect them. The goal of the data center is to bring the data and collect it and then monetize it and use it. And now this connectivity of these data centers or data centers themselves provide these services. And these services are centered around data. That's why we call this data center, right? So you have server, storage, networking, and software running in the data center that provides cloud computing. You have databases, data services. Mostly it's consumer services today. So most of the user of data is your cell phone or your computer, TV connected to a data center, and that cloud service gives you data, right? The data could be media streaming, data could be e-retail, any form of use you have for your data, that's the consumption, and that consumption creates the economy around cloud computing. Of course, the second user of data is analytics and intelligence, so that data center is also running AI internally to figure out what's happening with data so they can improve the services and create value. Next. Okay, so data centers come in various scales. You have the public clouds. Those are the hyperscalers. You have them in the US, Microsoft, Amazon, Google, and they're also in Europe. They're also in other parts of the world. China has its own versions. They have Alibaba, Tencent, Baidu. Then you have the private clouds that are in the middle. Those are smaller. Those are typically enterprise clouds, but they could also be government clouds. I think in the introduction today, we heard about government sort of use cases for the clouds. Those are also connected to the back end, but you can build infrastructure to monetize or optimize the use of your own services as well in the form of a private cloud. And then you have the edge clouds, which are closer to the source of data and closer to the user because they have not only data privacy framework requirements to make sure that you could keep your data with you, but also fast decision making and real-time requirements because you have to be able to return a request within a certain contract with respect to response time. Right? So if you have time-sensitive services, you'd also want to keep those closer to yourself in edge clouds. Hyperscalers run edge clouds in Europe. They also have bigger data centers, but the edge clouds for hyperscalers, if your public cloud is about 0.5 gigawatt, your edge cloud is about 100 megawatt. Okay. Next. Okay. Not to confuse data centers with supercomputing. Supercomputing are also campuses that we support at the government level. We build supercomputing to help with scientific discovery, but it's also for national defense. And it's basically a computer that runs as fast as possible to solve one problem. The goal of the cloud is to build infrastructure so we can host as many customers as possible and run them smoothly through the cloud with a given contract. But that contract is not that you would run through that as fast as possible. The goal is to have a return on investment for the data center to be able to then host as many customers as possible. Okay, so you're running massive computing services for your customers. You're not trying to solve one scientific problem, whether it's drug discovery or whether it's oil exploration, any form of scientific computing. Next. Okay, so I think I've made this point now clear. Why cloud computing? It's all about money, right? So you want to bring the cost of computing down, and this is the way you do it. Cloud computing offers faster innovation, flexible resources, economies of scale. You're not building the best technology ever, but you're building a massive technology built with super cheap components. And speed, because you can now launch an application as a user of the cloud. You can create application, launch them as fast as possible. That's also related to productivity because you don't have to worry about running your own servers. You don't have to worry about hardware. You don't have to worry about all the software needed to create computing. You're just at the top level launching your own application as fast as possible. Scale means you could basically pay as you go for how much computing you need. You don't have to worry about then provisioning enough servers in your own basement to budget for what is expected. So you could basically scale that requirement for computing and pay as you go. It's a pay as you go service. Performance, of course, now the big cloud providers, they're among the top most valued companies in the world, so they also push technology. Those technologies are proprietary. They're not going to be available to the outside. So if you want to build your own, you have to go with commodity technologies. If you're using one of those cloud services, you're benefiting from proprietary technologies, which are a lot more advanced than what's available to a commodity user, or what would be available, for example, to the government. It's faster, it's more reliable, it gives you productivity, it's good for everything. It's good for security because their technology is stronger, so they can make sure that your computing is also secure. Privacy is a huge question because if you go with a public cloud provider or any cloud provider that's not your organization, they're basically in charge of what you're doing. They have your data, they have your code, they have your AI models, right? So privacy is a huge question. If you build your own private cloud, then privacy is your own. You have sovereignty over your computing. Okay, next. So it comes in various flavors, right? On the left-hand side, private cloud, that's you build your own, and you build a campus, and you have your servers, you have your software, you have your application. That's a private cloud. That's your own, right? And multiple entities within your organization can use that. Of course, building that is harder today with state-of-the-art because commodity technologies are behind proprietary technologies that are only available to hyperscalers because hyperscalers are innovating also. And as AI moves forward, hyperscalers are also building technologies for AI that would not be available to you if you want to build your own private cloud. But you have 100% sovereignty over what you're doing. The other options are going public. Public means there are three forms of public cloud services available. One is infrastructure, which means that Microsoft just gives you the computers on the internet, and you run your own operating system, you run your own system software, and then you're on your application. So you have control over the system software and your application, and the provider controls everything else. Platform as a service is that you don't even bother running the operating system, which is the software needed to run the servers. You just deal with your application and your data. And software as a service is that they provide a service for you. You can imagine a token service for an AI where you have a query. You have a query to ChatGPT. They do everything. They just answer your query and you pay for that. So they own everything. They just give you a higher level service. Next. Yeah, infrastructure as a service, you rent. You rent basically what appears to be a computer on the internet. They give you access to that computer, and then you run everything on your own. Platform as a service, you use their technology to develop software. Google has its own, Microsoft has its own, Amazon has its own. You use that technology to build your software. You can run it. They will deal with everything else. That's good. What's bad is that once you use their environment to create your own software, you cannot take that software and run it with another hyperscaler. You have to rewrite the entire software for the new environment because they're all vendor lock-in for their own good. And software as a service, that you just use their software, so you're just the user. You're on social media as the typing, and that software is then given as a service to you by the vendor. Next. Just the last slide on, 2 slides, I guess, on this data center versus cloud. I was also asked to comment on, what is the adoption rate? Adoption rate of cloud in modern countries, according to some think tanks, it's going to be 85% in the coming years. I've collected this data from Gartner and Goldman Sachs. What is the market cap of the cloud today worldwide is $670 billion. That's $500 billion, roughly over $500 billion, growing at 17%. Data center investment is at about 280 billion. So you see that difference is that you're investing 280, you're getting 670 out of it. That's really what this cloud is about. It's an economic model. It's growing at the same rate. I actually did the calculations, and surprise, surprise, they grow at the same rate. Energy, it's about 450 terawatts worldwide. That's roughly the electricity of Japan, half of it, sorry, and it will be soon the electricity of Japan in the coming years. So that's all of Japan, half of it, that's 450 terawatts, is growing at 16% because we can squeeze a little bit out of that energy when we create more data centers by creating more centralization, more efficiency. Next. And just as a last sort of point here is this efficiency and emissions in data centers and its impact on the environment is super important. So we've also launched in Switzerland a label which is globally available to the world that precisely quantifies the efficiency and emissions of data centers, data center operation. And if you have any questions, I'm more than happy to answer them. And you could go to our website and see what we have. It's a navigator platform where we have calculators where users can measure their efficiency for the data center, for their IT stack, and eventually their emissions as well. Next. And thank you very much, and look forward to the questions on the panel.
Thank you very much, Babak. Really, we realize that cloud computing isn't just one technology, right? It's different types of infrastructures, of technologies, of service models, of economic models. So thank you for your presentation. As I said earlier, please feel free to drop any questions in the chat, in the Q&A. If you're online, we'll have some time at the end to answer questions. Now, I want to turn to Zoe, who is online, who's going to take a sort of slightly different angle, really helping us see the sort of global distribution of cloud computing and also putting it in the context of artificial intelligence. Zoe, I assume that you can hear us. Please, the floor is yours.
Can you hear me okay? Hello, everyone. Thank you so much for having me. Can I just confirm that everyone can hear me all right?
Yes, we can. I'm just, for the room, please use the little earpieces, and then you can turn the volume up with the vol button, and you can hear Zoe. All good.
Hi, everyone. Thank you so much. Federico, shall I share my slides, or is the team popping them up?
You can share your slides, please.
Okay, it's not allowing me to because I'm not the host of the call, unfortunately.
Then I think so we might just share them here. Is that correct?
Thank you.
All right, we'll share them from here.
Perfect. Thank you so much. Hi, everyone, and thank you, Federico, for that introduction, and Dr. Falsafi for that amazing overview to ground this conversation. So my name is Zoe Hawkins from the Tech Policy Design Centre in Australia, but speaking to you today from Delhi. As Federico mentioned, I will be adding another layer on top of this conversation to set the scene, which is talking a little bit about the geographic distribution of some of this technology, particularly looking at AI compute. Next slide, please. That's a little bit about where I'm coming from. So think tank in Australia, as I mentioned. Before jumping into AI compute, one little plug is for our Tech Policy Atlas. I know that the audience of this group is the Diplomatic Corps following tech policy developments around the world. So we've got a great resource there mapping those developments for you if that's of use. But now let's dive into AI compute and its relationship to cloud computing. Next slide, please. Yep, and so today what I'll be speaking you through in the 15 minutes that we have is essentially some of the findings of a recent paper that I've done with some colleagues. So this is just a page to provide you with the reference to where I'm drawing some of these insights from, and to acknowledge my colleagues, Professor Willy Liedenberger and Boshi Wu, who are my colleagues at Oxford University with whom I've done this research. Next slide, please. Dr. Falsafi's already done an excellent job of setting some of the scene, so I'll be able to power through some of my initial slides. But just to help contextualize, what am I talking about when we think of AI? There's a few core ingredients when we think about that. There's the data that goes in, the algorithms that that operate to produce the output, but also the compute that drives that operation. And that is the piece that we're looking at today. There are two core ways of thinking about how it's used. And I will say, for full disclosure, I'm a tech policy professional and practitioner and researcher rather than a technician. So I'm going to be using it at the hopefully a level of description that will be relevant for this political geography conversation. In looking at it that way, the two core functions that we think of when looking at AI compute in this research is compute as it's used to train models, so develop AI models and systems and how they work. And then there's a second element, which is using those models once they're developed to generate outputs. As Professor Falsafi already mentioned, this is very resource intensive, both in land, electricity, and also the semiconductors that are used to conduct these operations, some of which are advanced enough to support these AI operations. Some of those are referred to as graphic processing units, or GPUs, which originally in many cases developed for things like video games, but are now being used for some of our advanced AI models, which we'll speak to shortly. As was mentioned before, this is an incredibly expensive and resource-intensive operation and process, which means that for a variety of different reasons, this is a very finite and bottleneck resource for a lot of the AI advancement and development that's happening around the world. And all of it is leveraging, a lot of it is leveraging this global cloud computing infrastructure, which Dr. Falsafi was describing before. Next slide, please. So here what I have is a bit of breaking down the AI compute supply chain. So in order to be able to have, to be running an AI model today, what are some of the elements that feed into that? So on the far left-hand side, you have the companies that design these AI accelerators. So that's, you know, a very market dominant company here is the US firm NVIDIA. There are those that then fabricate, produce these accelerators. So TSMC and ASML leaders there. And then we have those that actually make that compute power available in data centers as compute. And those are the sort of platform as a service, infrastructure as a service, and software as a service concepts that we were just speaking about before. Next slide, please. And there's also the last bit there, which is those that then consume it. So people who use that AI compute power to develop and then apply these AI models. As you can see on the slide now, the places that provide and make available this AI compute can be broken down to a few different categories. What we were seeing is the race car in Dr. Falsafi's slide, the scientific supercomputing. They're really focused on that one problem. Then we've got those private compute clusters. So as was mentioned, you know, a company like Meta using this sort of power to develop and use their own internal AI systems. And then that third part, which is the public cloud compute. So really that like rental pay-as-you-go service that we were speaking about before. Next slide, please. And that's really the one that we're zooming in on, public cloud compute in this study. And what we're looking at is where in the world are we finding this resource? Next slide, please. So the research that we've done is to conduct a census of the six of the hyperscale public cloud providers, many of which were mentioned before. So we have 3 of the US firms, so Google, AWS, and Microsoft, and also Tencent, Huawei, and Alibaba. And what we've done is mapped the publicly available information through these companies' customer interfaces to understand where in the world, within their global cloud computing network, some of the leading AI GPU-enabled data centers are. So where in the world can you do some of this leading AI work? Now, what's worth mentioning is that the list on the side there, so that these are the chips that we're looking at. Specifically, we were looking at NVIDIA-provided chips, and at the time of this census, we included those that were their sort of AI advanced chips, noting that obviously that always moves on and we have the B200s coming through, but that list there at the time was sort of the cutting edge. Limitations on this study obviously is that we've picked one company providing like one company for the chip provision, and doesn't look at all the other options that are there, although I think that there's still a lot of value in the study given the extreme market dominance that NVIDIA does have in this space. Next slide, please. I won't stay on this slide for too long because I know that it's sort of quite hard to interpret, but essentially just want to show you that this is the sort of more raw quantitative findings that we had in terms of looking at the list of countries down the left, the cloud computing regions that are available from these 6 hyperscale providers in each of these countries, which of those have GPU enabled regions, so places in which you can do some of these advanced AI processes according to the scope that we're looking at, and then broken down by which of those chips, with the H100s being the most advanced, through the A100s and the V100s as the older versions through from 2017. Next slide, please. Okay, so when you actually try and convert that into understanding this in terms of geographic distribution, what does that look like? We've visualized it in this map here for you on the screen, which I hope you can see. The dots represent the cloud regions of each of the hyperscalers, and of all 6, and the different colors represent those levels of I guess sophistication in terms of those AI chips that I mentioned before, with the H100s being the sort of most powerful in this study, being the purple dots, which you can see aggregated around in the US, over in Europe, the lighter blue being the A100s, slightly more distribution around the world, and then the slightly older generation of the V100s with an even greater spread. Next slide, please. So I think that's a lot of numbers and then a bit of visual. So let's take a step back and think about what we found from this study that we thought was really interesting. So 39 countries actually do have 1 or more cloud regions at all, just to start with. And of those 39, 30 had cloud regions that feature the GPUs that we were looking at. So this is just looking at, that's quite a narrow group of countries already to begin with. What's interesting, but perhaps not surprising, is that China and the US together have almost as many regions as the rest of the world put together. So we can see a really strong geographic concentration, as Dr. Falsafi mentioned, coming through in terms of where is this power available in a physical sense. Again, the US has a lot of those most cutting edge AI chips located in its territory, and is the only country to have more regions having the A100s than the older generation of the V100s, which we see more of around the world. And across the world, only 15 countries offer A100s, which is just an interesting stat, and only 1 has the H100s. The rest are purely V100s based. So just looking at this generation of technology rollout and what does that mean around the world. Next slide, please. So what we've looked at is, if you take the assumption that the most advanced AI chips that are available in the study are the most important ones to be doing the model training that I spoke about at the beginning, you can, versus the slightly older generations, which would be more effective potentially for that inferencing work of sort of applying and using those models once developed, we create this concept of the compute north and south. And so the north is where they have at least some quantity of GPUs most relevant to AI development. So that's the A100s and the H100s. What we noticed in the 15 countries that fall into this category, outside of the US and China, is there was quite a strong analogy with what would be commonly termed the sort of the global north, with save from India, who's also in this category. So that's where we've come up with this analogy. In terms of the global south, this is the compute south. We're talking about the countries that have the V100s, those that are going to be really useful for applying the models. And those 13 countries reflect the analogy of the global south, apart from Switzerland, who actually sits in that category as well. What we're calling the compute desert is, I suppose, the countries that fall outside of both of those categories, and so currently don't have, in the scope of the providers in this study, don't host any public cloud AI compute at all for either training or deployment, which means relying on services provided in jurisdictions outside of their own. And that is a kind of conceptual model that we've just built out through this first iteration of research looking at a particular set of providers and chips. But we're just interested in exploring this idea of what does this geographic distribution of this compute power mean over the top of the cloud computing network. And why does it look this way? I think we can get into this in the discussion, and I'm looking forward to that. But there's obviously several theories that you could intuitively come up with as to why this is the case. But I think it's also, why does it matter? There's a growing conversation around, does it matter where this power is, for a variety of reasons, whether it's power to intervene from a government perspective, if it's the cost, both financially, environmentally, of these resources. So really looking forward to the conversation. That's a very rapid run through of our research on the political geography of AI compute, and I look forward to the conversation. Thank you so much.
Thank you very much, Zoe, for that very comprehensive overview. And I really urge anyone to read that study. It's really eye-opening study. We now have about 20 minutes for Q&A. Thank you very much, Zoe and Babak. All right, well, I think this is all the time we have for this session. This is not the end of the event. If you're online, we will have a coffee now and join again at 11:30, where we will go into the international security implications of cloud computing. I want to thank Babak Falsafi and Zoe Hawkins for joining us for this session, and please join me in a round of applause for our speakers. So yeah, thank you so much, Zoe. Have a good rest of your day in Delhi, and for everyone in the room, we'll be back here at 11:30. There should be a coffee outside. Thank you.
Thank you.